Welcome everyone to the introductory video of Consteel version 17. Let's start the program right away. First, we see the new opening screen, where the winning model of this year's Steel Lion competition is showcased, a velodrome roof structure. From now on, we will showcase models that win awards in our Steel Lion user competition every year. I encourage everyone to participate in this user competition. As Consteel starts, we can see the project center. On the right side, it's always worth checking the info panel, where we announce the latest events, our training sessions, or if there is new material on the website in the knowledge base. Here, you can find a link to the summary description of the new features of version 17, which we will open right now. You can read about the new features developed for version 17, primarily focused on making software usage more convenient, including functions related to model management, modifications, result processing, or script writing. Let's take a look at the innovations in Consteel. I'll open a previously saved model from the cloud, and we'll make various modifications and calculations on this model. Our model is a small canopy consisting of hot-rolled primary structure with a cold-formed purlin system. There is a cutout in the roof and tie rod bracing. The load transfer surfaces and some of the loads are already defined. Before we start working, let's save a model version immediately by pressing the History button. Versions can be named and a description is also possible to add. We'll create this version and so we can track the changes. I want to save at least one more version after the modifications are done, so we can demonstrate our new comparative feature on SteelSpace, which works with these saved versions. Returning to the model, one of the most noticeable new features is the automatic model portions on the right-hand side. Previously, only custom portions were possible to be defined in Consteel. After reviewing many models, we noticed that our users often define model portions based on very similar principles. Based on this, we selected some criteria to automatically create portions that are always updated to the current state of the model. For analysis, only user-created custom portions can still be used. Currently, you can filter bar members by section, even displaying different sections simultaneously. You can also filter by materials or by placement, meaning the orientation and plane in which the members are positioned. If there are results, you can filter the elements by the dominant utilization. Plate elements can be filtered by thickness, material, and also by placement. Let's try this feature. We select the CHS sections, and we want to change the end releases of these elements. Since this is just a view filter, we still need to select the elements. We immediately see another small innovation. The start and end points of the bar members have separate markings in yellow and magenta to make it easier to determine which is the start and which is the end point, especially useful when defining different end releases. Now, let's set another release type and return to full view. Another change on the right panel, besides automatic portions, is that the Model Content tab has disappeared. However, it can be brought back by selecting it in the View menu when needed. There's one more new feature. The Hide function has been added to the Custom Portions tab, which hides the selected objects from the current view. This is the opposite of the submodel view. Let's go back to the complete model and check another selection option. I select a purlin element, and I want to select all the bar members in the model with the same cross-section. The new function allows us to select all elements in the model with the same attribute as the selected element, based on any attribute. This can be done by double-clicking. So if we want to select bar members with the same Z section now, we double-click on the section, and it selects all 28 purlins. But we can do the same for releases, double-click and now all members with continuous release is selected. Returning to the purlins, we can see that the material is incorrect here, as it is not set to the coated steel used for cold-formed sections. Let's change this now, again with a new function in the section administrator. If we want to simultaneously change the material for multiple sections, in this case, all Z sections, we can do this with collective selection and a right-click. We select a material suitable for cold-formed sections and approve it with OK. The material has been updated for all such cross-sections in the model. The next feature group I'd like to mention is in the MyDescript environment. Many new features have been added to our internal environment where scripts can be written and executed. This has already provided efficient assistance to our users earlier. The Descript manual on our website already includes new features alongside with the previously existing commands. The command reference page summarizes the commands, clearly indicating which commands have been newly implemented. In addition to new commands, several existing ones have been extensively expanded. For example, under Create, which involves creating model elements, many new objects have been added. Get command allows us to retrieve information about many new things. And the Set and Filter commands similarly list the new features. One of the most important new commands is that now you can create these cold-formed macro-type sections with all kinds of stiffeners. This is a big step forward because now these sections can be handled at the script level, not just with manual modeling. Let's see an example. Let this be this Z section. Here, as everywhere, there is a sample code that we can easily copy and paste into the MyDescript editor interface, starting a new code. We can immediately run it, and we do that now. The script creates a new cold-form Z section in the section administrator. Opening it in the section module, we can see that this sample code includes various options. It created this section with right and left-facing stiffeners and various edge stiffeners to demonstrate how various settings can be handled here. While we are in the Descript environment, let's create wind loads for this open roof structure using a built-in code. There is a code called wind load on monopitch canopy, which allows us to generate wind loads, precisely for such structures. If we go to the Loads tab in Consteel, we can see that this wind load is currently missing among the loads. I'll turn on the Load Transfer Surface Visibility because we need to select it. Let's start this Descript function. This is an Excel-based function that starts by opening an Excel file where we need to define input parameters. Wind load-related parameters and geometry-related parameters must be defined. These are already set now, so we can accept them. The dialog only contains checks to ensure everything is okay, and if so, we can start the function. It shows what we need to do. First, we need to select the load transfer surface. We can do this by clicking on the Select button, left-click on the surface, and then closing it with the right mouse button. We have selected the load transfer surface. We also need to select these 3 points on the load transfer surface. The first one here, the second on the right side, and the third on the right side at the back. Once this is done, wind load generation starts. The code ran successfully, and we can view the result. It automatically created 2 load cases, one with wind pressure and one with wind suction. Our model can now be considered essentially final. Let's take a look at various load cases. We can see that all of our loads are surface loads defined on the load transfer surface. These can also be viewed in a distributed view. An important feature in version 17 is the significant change in handling distributed line loads derived from surface loads. Now, these loads can be individually selected and their attributes can be viewed: load value, eccentricity, and any other attribute associated with a distributed line load. If, for some reason, we want to modify an attribute of a particular distributed line load, we can use the next new function to separate these distributed line loads from the surface load. After that, they continue to exist as independent line loads, and any of them can be freely modified. So, the distribution of line loads from surface loads still happens automatically, but now there is the possibility to modify the details of the generated loads after exploding the surface load. For example, if we see that we are not satisfied with the load distribution in this area and want to change it, we first select the specific load. A new attribute appears in the Object Properties window, Linked Surface Load. This means that the selected distributed line load is associated with the highlighted surface load. A red X appears in this row, allowing us to detach the distributed line loads from the surface load. If we press it, a message appears that, in this case, the surface load will cease to exist, and all distributed line loads derived from it will be independently manageable. Therefore, from now on, any exploded load essentially functions as an individual line load and any parameter can be freely modified. If we want to modify, for example, these loads around the small opening, we can filter this view with the automatic model portion. We select the loads and set their values uniformly to -1.5. Now we can say that our loading is acceptable. Another typical necessity for modification is when the point of action of a load is not the same as what we set at the load transfer surface. At the load transfer surface, it is possible to define eccentricity in the local z direction. This eccentricity is valid for all surface loads acting on the load transfer surface in all load cases. In this case, we want to define installation loads at the bottom of the purlins according to the data provided. Here, too, we can select the load, explode it, and once again receive a message about exploding the entire surface load. Now, if we select all our loads in the load case, these will appear as simple line loads that can be modified individually. We can now modify their eccentricity collectively. Once we have defined the loads accurately, let's move on to Load Combinations dialog and create the necessary load combinations. We want to create ULS load combinations as well as SLS load combinations. There is a slight change in this dialog as well. We introduced new serviceability limit state types based on whether they include permanent loads or not. Let's create both types of characteristic combinations. All load combinations could have already been generated in Consteel. Now we've essentially just organized them into limit states. It can be seen that ultimate limit state load combinations have been created, and combinations related to both types of serviceability limit states have also been created. These include both permanent and variable loads, and the only difference is that permanent loads, in this case only one load case, are considered with a safety factor of 0. This will be interesting for serviceability limit state checks, as generally different limit values need to be used for the two types. Save the load combinations and proceed to calculations. Start the Analysis Parameters window. Turn on the usual analysis types for both limit states, and start the calculation. The analysis results for all load combinations are now available. Now, let's proceed directly to design and initiate a check in the usual way. Enabling cross-sectional and stability checks. We have reworked the representation of the results. On the one hand, we have merged the two limit states that were previously on two separate tabs, so now the results for both serviceability and ultimate limit states will be visible at the same time. Another significant innovation is that results for every load combination are now available. This means that not only the dominant results are visible, but also the design results for each load combination can be separately retrieved. The drop-down menus have also changed in line with the new structure. First, there is a selector where you can choose between utilizations and pre-designed parameters. As pre-designed parameters, in this case, results related to slenderness can be requested, and for each combination, they can be checked. With the other option, utilizations can be examined. Here, individual checks can be selected, and in the next one, you can filter by combination similarly to the structure of the analysis results. Let's run some checks for serviceability limit states. There are many new features here as well. Firstly, the two types of combinations have appeared, as mentioned, and for both types, limit values can be defined separately. In this case, we define a horizontal displacement check. It will check the displacement of the point based on the height of the point. We define limit values of h/100 and h/150. We must provide a reference level against which the heights of the calculated points are measured. This is now the z=0 level. We can also define a model portion to specify on which points the check should be performed. We will calculate this for the entire model now. The check button performs a preliminary calculation and shows how the structure is performing but does not save the results. Currently, it is visible that in combination 43, the utilization is quite high. The displacement is significant. We save the check with OK for now and close the dialog. Let's also define a vertical displacement check. In this case too, we can define two limit values, and we must provide a reference length. Let's take the distance between start of the console and its endpoint, about 5 meters. Here, too, we can quickly look at how we stand. Again, the displacements are quite significant, our structure is not really suitable. Let's save this check as well. If we go back to the summary window and press the Calculate button, Consteel will perform the saved checks, and the SLS results will also be included in the drop-down menus and the result grid. So now, it is visible that these are the dominant checks, and the displacements in the vertical direction at the ends of the consoles are quite large. All checks, for both ultimate limit states and serviceability limit states, for every load combination, are visible here. The dominant calculation result shows the dominant utilization for all cross-sections from all load combinations. Moreover, it is now possible to access individual checks for each load combination separately for all structural elements. This means, for example, that for each load combination, the utilization of all structural elements in the serviceability limit state is visible. We no longer show only the dominant value but display all load combinations. Additionally, results for horizontal displacement checks can be separately checked for various combinations, and similarly, vertical displacements or the dominant SLS check can be individually examined. All of this is now seamlessly integrated with all design results here on the Global Checks tab, eliminating the need to view our dominant results in two separate tabs. At these SLS results, you can right-click on the grid to bring up the panel of the respective SLS check, based on which this calculation has been performed. Let's make some changes to the structure to improve the situation a bit. Currently, the columns are very weak. It is evident, for example, in the critical SLS combination 43, that the columns are deflecting significantly, resulting in large displacements at the roof. Therefore, let's change the size of the columns, select all the columns and change to a stronger section, for example, HEA 200. Run the analysis and design again. It still doesn't fully meet the requirements, but the situation has improved significantly. There are no longer utilization values of 500%. Now, we can show where the structure does not meet the requirements. For example, elements with utilization above 110% are problematic, and those between 100 and 110% are these. The new auto portion function identifies the highest utilization on each element and groups the members accordingly. These are the elements that are well utilized. Here are the elements with lower utilization. Regarding member selection, there's another new feature. If we enable the ULS utilizations, we can mark rows in the results table and, with the right mouse button, select the elements associated with those rows. It is visible in the Object Properties window that we selected two bar members. In the Structural Elements or Geometry tab, you can see that these are two beams on which the selected utilizations appear. So, elements can be selected either from the results table, or filtered by auto portions based on the dominant utilizations. After the changes, let's save another model version. Open the History feature and create a new version. Enter a description, such as new sections, new end releases, and new loads added. Create this new version of the model. So, we continue working in the same file, which can always be opened, but now there are different versions. For this model, there is an initial version, and there is this modified version, which can be viewed in SteelSpace, where additional features are available to analyze the model. Let's switch to SteelSpace. We are already logged into the SteelSpace account. Here, you can see the model for which we just saved a new version. The model opens by clicking on it. The second saved version of my model is immediately visible here. In SteelSpace, we can also filter by sections, and it highlights the elements. In the display options, a new feature has appeared, the clipping plane, which allows us to immerse a bit into the details of the model. We can make cuts in all three directions. For larger models, this can be a very useful visualization option. Now, let's take a look at the compare function. Select a version and click on the Compare Version button. We want to compare the initial version, NR1, with the modified version 2. In the next step, there are many new features. Here, you can specify the objects or attributes that the software should consider during the comparative analysis. So, if we are only interested in the differences in bar members or only in the differences in loads, we can leave only those selected. By default, all handled objects and attributes are included. You can also select attributes by object type, for example, separate attributes for beams, such as changes in section or material, or changes in end releases. We leave everything selected and start the comparative analysis. You can see now the result of the comparison. Using the slider, you can switch between the two models. If we zoom in a bit, we can see that the section of the column has changed between the initial Model 1 and the modified Model 2, and this is well visible in different views. Clicking on this column section, you can see on the right, in the properties, that there are two versions. Changes of different types, addition, deletion, and modification, are indicated with different colors. Here, HEA 160 has become HEA 200. If we click on such a bracing element, you can see that the end release of this element has changed. These were the new features in SteelSpace. A deeper and more complex comparison of model versions are possible now due to the new developments. This concludes the demonstration of the functionalities on this model. I would like to show the next feature on another model. This is the new functionality related to tension-only members. In this model, you can see that tension rods are defined in several places. The problem with tension-only members is fundamentally that they are nonlinear elements, as they have zero stiffness under compression and full stiffness under tension in calculations. These nonlinear elements are difficult to combine with linear calculations, either with the first-order calculations or stability or dynamic analyses, which are linear eigenvalue tasks. Therefore, these elements need to be linearized in some way. If we look at this structure now, a typical problem with these tension rods is that if we have a load that causes compression in both elements applied in pairs, as is the case with the elements here on the end walls, both of them would be under compression. As a result, these elements are excluded from the first-order calculations. In this case, there is no problem because they don't contribute much to the planar stiffness, but if there is also a stability result, since these bracings no longer exist, we get an unrealistic shape for loss of stability, with a very low critical load factor. In practice, one of the rods will be in tension in this case, so this shape in the reality cannot happen. This doesn't always cause a problem, but when it does, we can select these tension elements and convert them to the new element type called X-brace. In this case, if we rerun the calculation and return to the full model, we now get the correct buckling shape. These elements will now work in a way that they will give exactly the same behavior, so they will be under compression, and they will be excluded in first-order analysis. Here, as I said, there is no problem because the deformations are entirely realistic, and the element works fine. However, these elements are not completely eliminated from the linear stability analysis, but all these X-brace type tension rods are considered in the classical way, with half cross-section, because they are usually defined in pairs, even if they are not in the same place. However, to prevent these from buckling, as they would likely buckle under a very low compression load, they are automatically excluded from the model for which the stability analysis is run. So, on the one hand, their stiffness appears with half cross-section in the stiffness matrix, so these end walls won't lean out, the bracing will work. On the other hand, they are excluded from the geometry matrix, so stability analysis is not relevant to them. Thus, the actual stability analysis is performed, and in this case, it can be seen that usual lateral torsional buckling shape of the frames will be dominant at a significantly higher, already acceptable critical load level. Following the developments in Consteel, I would also like to demonstrate a new feature that will provide innovation in the import-export processes with structural engineering software. It is often important that if a user works with multiple structural engineering software on a project, there should be some kind of connection between them. This can be achieved in various ways. We have now developed a completely new environment and procedure for this through our API, and we have implemented the first example of this with the Axis VM structural engineering software. Let me show you this now. I opened an Axis VM model here, which is available on their website. It's a sample steel hull model. In this case, you need to install a plugin if you want to use our new feature. This plugin can be found on the Consteel website, under the Downloads menu, where you can also download Consteel installation packages. We have a new tab for plugins. Here, you can find the installer packages of additional programs that are not part of the Consteel installation package, but are necessary for certain functions. We have placed the Axis VM converter here. Panviolin is also available, and there is a small program needed for users with USB dongle protection. So, you can download the converter plugin here. It needs to be installed in the same folder where Axis VM is installed. In this case, the next time you start the software, under the Plugins menu, you will see the Consteel converter. If you launch this, a window appears where you can enter some parameters. For example, whether you want to convert the entire model or just selected elements. You can define a name. It suggests the Axis model name by default, which we keep. And you can specify a path where it saves the file format that exports this Axis VM model. Clicking the Export button starts the export. 2 conversion files appear here. And the file location opens. Currently, there are conversion files for materials and cross-sections. These are also located in the Axis folder and can be individually modified or expanded. So, the SMADsteel file is created as a result of the conversion, and we can now open it in Consteel. When opening, you need to select the SMADsteel file type, because this is the file format that these structural analysis software conversions will use. SteelSpace also uses this format. Let's open this model. Regarding the conversion and this environment, it's essential to know that a multi-step file conversion is carried out through the API. In the first step, based on the section and material names in the conversion files, it tries to identify objects and matches the identified objects one-to-one with those in Consteel. So, for example, if it finds an HEB 200 name in Axis, it matches the cross-section of that with HEB 200 in Consteel, as seen here with the columns. The conversion also works similarly for materials. In the case of support and end continuity types, there is no conversion file, but it uses the default types in Consteel. The second level is when it cannot find a match by name, it looks for a match in object type and tries to match the attributes within that type. For example, if it doesn't find a name for a steel material, it looks for the attributes of the steel material, such as elasticity modulus, yield strength, etc., and creates a new object in Consteel with these parameters, like a new steel material quality. The third level is when it cannot create the specific object type. For example, if it cannot find a cross-section for a particular beam and cannot assign it to a cross-section type either, it adds a default object, like an unrealistically large pipe. During the conversion, a detailed import log is created for the imported model, showing which elements were imported. For example, here are the cross-sections, such as HEB 200. It can be seen that the matching was done based on the name, so it found this He200B in the conversion file, which we use as HEB 200. The other attributes are also listed, also for materials. If something is not found in the Axis API or in the API of the other structural engineering software, Consteel takes default values for that. It doesn't necessarily include every parameter, all of these can be viewed here. Additionally, the other software may have attributes that we may not know how to handle or that we don't need. Unimported attributes are also displayed. Generally, we aim to implement this structure, this environment in import-export processes, for interfaces with structural analysis software. So, as a result of the conversion, this model has been created, our bar members are present, the supports have appeared exactly as an Axis VM, and various loads are also there. Here are the load groups. I'll delete this load group because this is the default load group in Consteel. So, the load groups and their corresponding load cases have all been imported. We assign the self-weight to the self-weight load case. The load combinations, created with names from Axis VM, have also been imported. This is again the default combination, I'll delete it now. So, 2 SLS and 2 ULS combinations were created. The loads themselves also appear nicely, the snow load and the wind load are the same as in the Axis model. Essentially, this is a ready-to-run model. I'll turn on the first-order calculations for all load combinations, and we can run the calculations nicely. Let's now look at an envelope figure of bending moments in ULS combinations. You can see that this is the bending moment diagram. The minimum and maximum values are in the result table. The maximum negative moment is minus 153 kilonewton meters. And the positive maximum is 123 kilonewton meters. These values are the same as in Axis VM if we look at the min-max values for bending moments from all combinations. We can see that here, too, the moments vary between 123 and minus 153. So, the results of the first-order calculations can be nicely reproduced in Consteel software. This means that the members and releases and supports have transferred well. It is important to note that we would like to extend this environment to multiple structural analysis software. Also, among the developments for the next year, the renewal of import-export processes will be very dominant. We have come to the end of presenting the new features of Consteel 17. I would like to recommend once again to everyone to read our summary of the new developments on our website. I hope that we have been able to develop useful tools for your work. Thank you very much for your attention.